Okay, so at the end of last lecture, I had defined this moduli space of, well, I said there was a moduli space of stable log maps. What I want to do now is to give some intuition as to what kind of extra information is actually hiding in a stable log map. So the very first example to look at is just take a pair xd. So our x is smooth, so D contains an x smooth divisor in smooth x. So here's the picture, here's x, here's D. Now, let's start with just an ordinary stable map. So maybe we have some curve sitting inside x, like that. So the map is just an inclusion map. And let's think about how we can try to enhance this to a log map. So here we're going to use the divisorial log structure on x. So in this case, we can actually just put a divisorial log structure on D. I'm sorry, on the curve C, or C. And remember, so if we take C with some divisor, which will be some set of points P1 through Pn, if we want a morphism from this divisorial log scheme to this divisorial log scheme, so there exists such a morphism if the inverse image of D is contained in the divisor here, P1 through Pn. So this is going to force this point and this point, being the inverse image of D, to be marked points on the curve. So maybe this will be point P1, this will be point P2 on the curve. And then there might be some other marked points, P3, P4, but we don't care. I mean, we only need inclusion here. So all the intersection points with D in this picture have to be marked points on the curve, assuming that we're using the divisorial log structure on this curve. Okay, now let's take a little look at what's happening locally at one of these marked points. So this induces a map on the level of the monoid sheaves, on stalks of monoid sheaves. So we have F flat from the stalk of X at the point F of Pi to the stalk of C at the point Pi. And that in turn descends to give a map of Gauss sheaves at the bar flat from M bar X F of Pi. I think the fire alarm is being tested. I'm going to assume it's a test and I'll leave the building. Good, it was a test. Okay. So we get a map like this, and provided that, I mean, what is the Gauss sheaf on X? It's just a copy of N along the divisor D. So provided that F of Pi is in D, then this stalk is just N, and of course this stalk is also N. So we just get a map from N to N, which I'm going to call.
Maybe. Okay. So there was a 20-second freeze.
Okay. Let's switch to Google.
Oh, okay.
Yeah, I think the dealing with reverberation during the talk is better than dealing with freezes.
Yeah.
Okay. So give me a second, and then to bring up the Hangouts, and then we can. Then you can call me.
Sounds good. Yeah. Well, I mean, I
Okay, then I'll try to call you. Yep. I never remember how you actually. Okay, so we're hopefully back in business. Am I coming through?
Yes, it's a little bit weaker sound than we need. I can just change this on how much here. Well, it should we just move forward. It should be fine. The video quality is quite nice. So sorry for the interruption.
Okay, yep, no problem. Okay, so let's see, where was I? So we get a, let me recap, because I don't know where I blanked out. So we have the induced map on stalks of ghost sheaves, sorry, of the monoid sheaves, and then that descends to induced map on the stalks. So I'm, provided that the image of PI is in the divisor D, this stalk is just N, and this stalk is always N because we're using the divisor log structure at the PIs. Now, I'm going to give this map a name, use of PI. And what does this mean? Well, if you think about what's going on here, let's let T, a local jet equation, for D. So, or T equals 0 local equation. Now, because T then only vanishes along D, it's an element of the ghost sheaf, it's an element of the monoid sheaf MX. You can think of T as lying in here. Now, what's this map then? For the divisor of log structures, that just maps to F star of T. Now, F star of T will be, if you take a local parameter, so U, V, a local parameter for C at PI, so a local coordinate, then F upper star of T, the composition of T with F, is necessarily to form some invertible function, phi, times some power of V. And that power of V is precisely this number UPI. Because what's happening is that the image of T in the ghost sheaf is 1, because T is the local equation. The image of this then in here is UPI, and that's just records the order of vanishing of the pullback of T at the point PI. Okay, so that's really just the order of tangency here. UPI is the order of tangency curve C. The order of tangency of the curve C at PI with D. And notice that this actually even makes sense for those points which don't map to D, is for those points, if f of pi is not in D, then you just get 0 mapping to n, and of course that's the 0 map. So in that case we say the order of tangency is 0, and that just means that the point's not mapping to D. Okay, so in other words, the combinatorics of the log structure, which is hiding here, as we saw, this was corresponded to last time to tropical information too. The combinatorics of the log structure encodes orders of tangency with divisors. Now, this picture, so the study of Gromov-Witten invariants where you impose tangency conditions with the divisor has a rich and long history, going back to Lee and Ron and Parker, and then Jun Lee gave some algebra geometric definitions. There's always a problem in trying to define what are called relative Gromov-Witten invariants, where you're working with some tangency conditions with respect to smooth divisor. This is a perfectly nice, easy type of curve to consider, but if you want a proper moduli space, a compact moduli space, you have an issue that this curve might fall into D. If you deform the curve, it possibly might fall into D. Then you no longer know what tangency order means, or some irreducible components. It might split up, and some irreducible components might fall into D. So the solution, the old solution, for example, that Jun Lee implemented, was a really quite complicated picture where you had to degenerate the target space as well as the domain to keep track of how irreducible compounds falling into D were really still, in some sense, tangent to D. So the great advantage of the log picture is X remains fixed, and it's the information, the log morphism, which really remembers everything. Now, let me say that in general what contact orders are. So in general, given log stable map, sorry, that's exactly what I said last time, I never say. Stable log map. Given a stable log map, say f from C, P1 to Pn, X, we get then, just as before, we get a morphism, homomorphism of monoids from n bar X, f of Pi, to n bar C, Pi. And remember, at a marked point, by the way, this is living over some, sorry, wrong way here, living over some point W, say spec K, with monoid Q. So this, remember from our structure theorem for log smooth curves last time, this has a factor Q coming from the base, from W, and then it has an extra n factor recording the order of zeros of functions at the point Pi. Now you can then project by the second projection to n, and this composed map, this is purely a bit of combinatorial information concerning the log structure, the ghost sheaves. This is the map we call UPI. So this is a generalization of this UPI. Of course, so here Q was 0, so we didn't have to project. And this is what we call the contact order at Pi. So I'll show you in a minute how that shows up in some examples. So you should think of this as the way that the log structure remembers orders of tangency. And the nice thing about this is it allows orders of tangency with more than just one divisor. Okay, so let's go to an example I promised last time. And this is the example where x will take us a target xd, which is p2, and with respect to the normal Crossman's divisor given by, say, the coordinate lines. 3 lines in p2 forming a triangle. So here's our domain, and let's take a look at genus 0 curves. Genus 0 and degree 1. Now, if you think of what a general curve of degree 1 is, it's just a line. Again, we're in exactly the same situation. It's just a slightly more complicated picture than this one here. Since we're avoiding any of the singular points, nothing is radically different to any of these 3 points. You're forced to mark these 3 points in order to have a logomorphism. But once you do that, you get a map from the P1 with the divisor log structure given by these 3 points to xd. And then the contact orders just record the fact that this point is tangent to this line to order 1, i.e. transversal. This point is transversal to order 1 to this line, and this point is transversal to order 1 to this line. Okay, so not very interesting so far. But now we should keep in mind that this moduli space is supposed to be compact. So let's see what happens as this curve gets deformed. So the first interesting thing, there are a couple of interesting things. One possibility is that this line moves so that it passes through this point. So let me just try to use some different colors. Let me know if it's doesn't show up well. So, for example, I could degenerate the line to this blue line. Now, over here, we still just have an ordinary marked point, but something has gone wrong over here because these 2 points have come together. And of course, marked points have to be distinct. So even already in the ordinary Gross-Witten world, the way you deal with that is you have to bubble off a component. So you're going to have a component sitting like this, now with 2 marked points on it. And this line, well, it's not a line, this P1 is contracted here. So this is still a stable curve because there are 3 special points on this contracted curve. Okay, so then the proof of properness of the stable log bound moduli space says that actually there's a way of putting a log structure on this so that you still get a morphism. And now the log structure is more complicated. I'm not going to really tell you what it is yet, but there is a log structure which turns this into a logomorphism on the domain C. The base now is more interesting. The base is not just spec K, but spec K with some extra mono. In this case, it's just the standard log point. So that's one thing that can happen. Another thing that can happen is that actually this entire line could degenerate to one of the 3 coordinate lines. Okay, so for example, the line could degenerate to something that looks like this. Oh, by the way, sorry, I missed the most important point here. I had a feeling I hadn't said enough. We have these 2 marked points here. Now, if you look back at the definition of the contact order over here, what is the stock? So if this is a P1 and this is P2, let's look at the map from M bar X f of P1, say. So because it's this point, there the monad is n squared, because we have two divisors passing through that point. So this is n squared, and that maps to, well, by UPI to n. And the point is that there are two choices for this that really have to do with the fact that one of these points you should think of as being tangent to the first one is tangent to the second one. And these maps are given by either, say, UP1 equals 1, 0, so just projection on the first coordinate, or UP2 is 0, 1. And so what that's saying is that actually this map remembers the fact that P1 is tangent to this divisor to order 1 and this divisor to order 0, whereas P2 is tangent to this divisor to order 1 and that divisor to order 0. So even though the point is actually mapping, each point P1 and P2 is mapping to both divisors, the log structure knows it's not really mapping to those divisors. It's not, it's only mapping to one of the two. So it takes some getting used to, but it really does record this information, even though you seem to be, if you just look at the scheme level, you're losing information about tangency. Okay, so going back to the case, of course here we have 3 points. This point is somehow knows it's just transversal, so order of intersection, tangency 1 with its line. This point knows that it's just order of intersection 1 with this line, and this point with intersection order 1 with this line, even though the whole curve is falling into this line. And then this point, of course, is now free to move. So you actually have, for this line, you still have one parameter family of possible curves. And in particular, that degenerates, so you have one last picture where the point that can move falls into either this corner or this corner of the triangle. And again, if this moves over to here, you have to bubble off, so you get a curve that looks something like this. Again, this P1 is contracted here, and these 2 points, this order, contact order, remembers the fact that one of them is still only mapping to here, and the other one is only mapping to here in some sense. Okay, so the contact order is some additional, very important combinatorial information telling us how the points interact, how the marked points are supposed to interact with the log structure, and in the divisorial case, really what the orders of tangency are. Now, I could have posed, just to end this example, I could have actually posed a completely different question, enumerative question, by posing a different kind of contact order. I could have only considered curves that look like this, with 2 mark points, where here, UP is given by 1, 1, in the sense that this point is supposed to be tangent to this divisor to order 1 and this divisor to order 1. And as a result, this point is not allowed to move away from this point. It's really constrained to map here, and then you get a 1 parameter family that might fall in here, fall in there, but it's nothing very exciting happens. Okay, so that's the first example. Now, what I want to say is next is a little bit more about this multi-space. So this is the example. some more on n beta x over s. So the first point is I was a bit evasive yesterday as to what information is in beta. So beta is genus, degree, and contact orders. So number of marked points also. So you have to specify the contact orders of the marked points, and then once you do that, you get a well-defined moduli space, which is proper. If you don't specify the contact orders, it's possible that this is not finite type. You might have an infinite number of complements. Okay, so that's the first thing, is that we have to specify the contact orders. The next point is that this is a log delete Mumford stack. So you don't need to really know anything about stacks for this discussion. It locally looks like a scheme modulo of finite group, but it does not classify all possible stable log maps. So let me show you why this is, in some sense, an impossible task if we want a finite type moduli space. So suppose we have a stable map, and I'm going to stable log map, and I'm going to just, for a second, include the monoid sheaves in the diagram. So we have some stable log map to X, which is a diagram like this. Maybe you have something down here too, I don't care. But now let's soup this up. I'm going to just change this very slightly by adding the constant sheaf n to the r to the monoid sheaf MC. And then I can do exactly the same thing down here, but I don't change x. I don't want to change the particle. Now, the point is, giving a logomorphism means we have to give a map from here to here. We already have a map from MW to MC. We just take the identity on the NBR component, so we still get a morphism. Now over here, we had a map from MX to MC, which is a subsheaf of this, so we just stick with the same map. This n to the r is doing nothing whatsoever, it's just noise. But r could be anything. So you already see there's a countable number of choices of possible log structures for the same family of curves. So if you really wanted a stack that classified all such diagrams, then you'd be in trouble. It wouldn't be finite type. And even worse, this has infinite automorphism group once you put in an extra, at least r equals 1, so it wouldn't be a delete Mumford stack anymore either. So this was really the most serious problem in the theory. So Bernd first started thinking about log-Gross-Witten theory around 2001. I think he gave a talk on this at that time, even before Jun Li's papers came out. And then the problem was that log moduli problems weren't well understood. And it was largely work of Martin Olson and his thesis in the mid-2000s that allowed us to get moving on this project again. So the key point is that there's some sort of good notion of a basic log structure of minimal ones, which you do want to classify in the stack. So m beta n beta x over s classifies what we call basic stable log maps and which Bromwich and Chen call minimal. It's perhaps just a sensible choice of word. So let's fix, I'm going to define a basic, well, almost define a basic stable log map. So basicness is defined pointwise on the parameterizing space of the family. So what I'm going to do is first tell you what, well, I'll just tell you what basicness means at W is a point. So if you have a stable family here with W being spec K with a monoid Q, then I can tropicalize. So last time I showed you how we can make sigma of C to sigma of X, and we have sigma of W, and this was just the code I was calling last lecture, sigma sub Q. So we already saw in last lecture that this map is just a family of what we would call tropical curves, a family of dual intersection graphs of the curve with various edge lengths. So what we're getting over here, by functoriality, here's sigma of F, we're getting a family of maps of graphs into the tropicalization of X. So you'll get this in any situation. But so I'm going to give a rather loose, intuitive definition of what basicness means. Family is basic if this family of tropical curves is actually the moduli space well, rather, this is maybe badly worded. So sigma Q is the moduli space. Let me just write something. I'll try to explain it by example. So there's the moduli space of tropical curves. In sigma of X. Of a fixed type. So, well, yeah.
Can I just ask a question?
Yeah.
When I was reading your paper, I got the impression that you had to choose Q equals N.
Okay.
Could you clarify?
Yeah, so taking Q equals N is a way of sort of testing, probing the moduli space. Right, so if you have any monoid here, you can do a base change. So one thing I've very carefully avoided talking about is fiber product in the log category. Because fiber product in the log category is awful. But let's not worry too much about that. You can certainly define a map from here to here. Remember how you do that. That's sort of really just a question of choosing a element in the interior of Q dual, and then maybe a little bit of continuous data. So you can write down maps like this, and then you can do a base change. And then you get a curve defined over spec K dagger, over the standard log point. And this will give a one-parameter family of tropical curves, because now the tropicalization of this is just array. And in fact, it's really just one, because all the others are obtained just by rescaling. So that's how we probe the moduli space, and that's how we eventually prove that this the criterion I'm about to give you is the right one. Not sure that's entirely a fair statement, but yeah, close enough. So it's a useful way of probing the more complicated moduli space. Okay, so let me try to explain this in some examples. So maybe I'll do these. Change this back to the vanilla example where we just had so let's think a bit about tropicalizing these three examples. So first of all, the tropicalization of X, as we saw last time, P2 is a toric variety, its tropicalization is just the fan for P2, so there's the tropicalization of X. And the tropicalization of the curve C is, well, there's one component with 3 marked points, so we just get something that looks like that. And one way to think of the contact order is the contact order is telling you precisely how these rays, the rays corresponding to marked points, map into sigma of X. So this UPI, the contact order is UP, those are maps from stalks of M bar on X into N. In other words, they're elements of the dual monoid. So they're elements of one of these cones. So the contact order actually tells you what direction these rays should, or essentially what rays these things should map to in here. And the fact that here at each of these points we're just tangent to order 1 to the corresponding divisor, and the divisors correspond to these rays, means that the image of this is just this curve. Okay, so under tropicalization. You see there's no monoid. The monoid stop of the ghost sheaf is 0 generically along the curve, and that gives you then this point, the vertex of this has to go to the origin here. Again, it's just really reflecting the geometry that the generic point of this P1 is sitting inside the generic stratum of P2, and that generic stratum is indexed by the origin. Okay, so here there's no moduli space. This point here is just stuck at the origin. So when I say here the moduli space of tropical curves of a fixed type, one of the things in the word type that's important is which cone a given vertex has to map to. So in this case, this vertex maps the origin. The origin is a 0-dimensional cone, so that can't move. There's no moduli. And in this case, the basic monoid, so when I say basic monoid, it's the monoid Q here, which makes this a basic family. So here, Q is 0. There's no tropical moduli. If I go to this example, again, the domain and range look the same. But the fact that the generic point of this curve is mapping to the stratum given by this divisor, let's say that that corresponds to this ray, it actually says that this vertex maps over here into this cone. Okay, so essentially all the tropicalization is really telling you where the vertices map to, which cones the vertices map to, is just encoding which strata various the generic points of the curve are mapping into. Okay, so then the 3 points still map. It's exactly the same picture, that, and that. Because again, these rays have to be parallel to the direction, the same direction we had over here, telling us that these marked points are tangent to the correct divisors in the right way. So here we have some ability to vary this point. Exactly where this point goes isn't determined. We have a 1-parameter moduli space. In this case, Q is equal to N. Now over here, the picture is rather a bit more complicated because, again, we have the same same target space, but the curve is now somewhat more interesting because there are two irreducible components. So we have two vertices in the domain, one of which has 2 mark points, one of which is 1 mark point. So that's the domain. Now, this vertex is going to correspond to this thing. That still maps into the same stratum that we had over there. So we have one vertex sitting there. This vertex corresponds to this irreducible component, which maps into this 0-dimensional stratum, which corresponds to this 2-dimensional cone. So I'm going to draw this over here. We have a vertex there. And then we still have the same, that's not going to work. Sorry, that's not quite the right picture. This is the right picture. We end up with a picture like that. Now, I'm not explaining everything here about why it looks like that. What we do know is, of course, this edge maps to something, but you could easily make a mistake along the lines I started to write, where this edge goes sort of horizontally and connects to this. But it turns out that in the toric case, this thing has to be a genuine tropical curve in the old-fashioned sense of Mikulkin, where you have some balancing condition. So that forces you, again, I don't want to focus on this, but that forces the curve to look like this. And the balancing condition comes naturally out of log geometry. So here we still have some moduli. Once you believe that this is the correct tropical curve describing the image of the map here, you have some moduli. So in other words, this point can move up and down. It's constrained to lie on this edge. And this point can go anywhere inside this cone. So that means that you have the parameter of this length of this edge, and you have the parameter of the height of this vertex. So this gives Q equals n squared. And so the full moduli space would allow any position for this and then any length for this edge. Okay, so I hope that makes some sense. But really the guide is that tropical geometry tells us what the right log structure is on the moduli space. So that defines the notion of a basic log structure for a family over a point. And then in general, if W is an arbitrary log scheme, you just demand that each geometric fiber of the family should satisfy this condition. So it's nothing more. Okay, so once you classify basic log structures, you get a nice moduli space. And the point is that these basic log structures really capture tropical geometry. Okay. So that's the end of my survey of log Gross-Hacking-Keel theory. Hopefully this left you with some feeling. And I think this is a very good example to study. And again, make sure you understand it well. Okay, so now let's switch gears entirely. So I think so far my talks and Bernd's talks have been completely disjoint. And now I'm going to start finally talking about mirror symmetry. So my goal for the remaining, about 2 hours and 15 minutes worth of talks is to, first of all, describe a construction of mirrors to log Calabi-Yau surfaces. And this is the only part of my talks which is in work. It's not with Bernd. But as you'll see, many of the ideas here were present in our work. So I'm going to talk about this work with Hacking-Keel, and then I will explain tomorrow how, combining sort of all the ideas we've had up to this point, we can construct mirrors in much greater generality. Okay, so what are we going to do? So first of all, we'll fix a pair, so XD will X is a rational surface, and D is a anti-canonical divisor, and maybe I should insert here, projective, non-singular, rational surface, and D is a divisor in minus kx, an anti-canonical divisor, which is a cycle of p1s. So what I mean is just looks something like this. And I'm going to write the irreducible components as the di. So d is equal to d1 plus dot plus dn for some fixed number n, which I will carry throughout the notation. Okay, so the goal is we're going to construct a mirror variety to this. And the construction will be should look quite a lot like what you've already seen in Bernd's. So that, just as a quick example, which I'll carry through also, is the de Peso surface of degree 5. Degree 5. So that's sort of, you start with P2, you blow up 4 points, and you can find a cycle of 5, so minus kx, in this case, can be represented by a cycle of 5 minus 1 curves. So a de Peso surface of degree 5, classical fact, has 10 minus 1 curves on it. And you can find 5 of them. There are a number of ways of doing it. You can find 5 of them. So they're really lines once you embed the de Peso surface in P5. You can find 5 of them, form a cycle. And then there are some other, well, as I said, there are 10 minus 1 curves. Which I'm going to call E1, E2, E3, E4, E5. This has the property that EI dot EJ is delta IJ. So EI only intersects DI. The difficulty in drawing this picture is that the EIs intersect each other in some complicated way over here, so I'm not going to try to specify the precise intersection pattern, but if you make a graph with 10 vertices and draw an edge between 2 vertices if the corresponding minus 1 curves intersect, you'll get a famous graph called the Peterson graph. That's worth drawing if you've never seen. I can't draw it. Look it up on Wikipedia. Okay. So what's the first step of our construction? The first step is fairly easy to describe given the technology that we've been developing, is let's tropicalize X, or tropicalize the pair XD. So consider, I'm going to call this B. B is the tropicalization of the pair XD. So notice we put the divisor log structure on X. We tropicalize. And what do you get? Well, you just get one two-dimensional cone for each of the double points Right, so each of these double points has stalk n squared, so you get a two-dimensional cone, a standard two-dimensional cone, isomorphic in the first quadrant, and then those cones get glued together along edges corresponding to the divisors in the cycle. So you get some picture that looks something like this. And right now, this is just an abstract cone complex. And let me label these rays and label the two-dimensional cones, sigma 1, 2, sigma 2, 3, and so on. I'll always use indices modulo 5. So we have here's sigma 5, well, 6, or sigma, same thing, sigma 5, 1. I'll always think of indices modulo n in general. Okay, so there's some notation. The rho i's correspond to the divisor di, and sigma I plus 1 corresponds to the double point di, and you say di plus 1 under chocolarization. Okay, so now we're going to do something a bit better, which is I'm going to put an affine structure. There's a reason why we brought affine structures into the picture. I'm going to put an affine structure on the complement of the origin. So give b minus 0 an affine structure. So how do I give an affine structure? Well, I just have to specify an open cover along with coordinate charts. So let's let ui I plus 1, actually let me give a different name, let me use that later. Let vi I plus 1 be the interior, vi, be the interior of sigma I minus 1 I union sigma I plus 1. So I'm going to just take, for example, here, this would be V1 would be the interior of this red region. And I'm going to describe an embedding of that into R2. So let's identify the closure VI with the following subset of R2. So what we do is we take here rho I minus 1 would be identified with the ray generated by 1, 0. Rho I will be identified with the ray generated by rho 0, 1. So this cone here is identifies with sigma I minus 1 I. And then rho I plus 1 is identified with the ray generated by minus 1 minus di squared. And so here's sigma I plus 1. Where does that come from? It comes from, if this was a fan defining a toric variety, that toric variety would have 3 toric divisors corresponding to these 3 rays. And this toric divisor would actually be a P1. And you can compute in toric geometry easily the self-intersection of a toric divisor in a surface. And this is designed to make the self-intersection of this divisor coincide with the self-intersection of BI. That's all this is doing. Put another way, it's saying, let's pretend that XD is a toric variety and try to write down the fan. Now, if it's a toric variety, you can actually do that by just sort of successively putting in cones in such a way that you make sure that the self-intersections agree. And when you get back to the beginning, when you wrap all the way around the cycle, you'll get a fan. Now, if we do this to something that's not a toric variety with this toric boundary, then things go wrong. So let's see that. Let's do that in this example of the Delpasser surface of degree 5. Okay, well, what I'm going to do, I'm not going to just keep on writing those charts down. I'm going to just try to write down a fan for dp5. All right, so I would start with one ray, let's say row 1. And then row 2 is here. That's just 1, 0, 0, 1. Now, all the boundary divisors have self-intersection -1, so I just have to keep on writing down things that make that happen. So it turns out the next ray, row 3, that should be -1, 1. That fits with what I drew over here. Di squared is -1, so I get a -1, 1. Okay, so now, so far we have this bit that fits with that. Now, you can do, if you want to find out where row 4 is, you can either do some sort of linear transformation to turn this cone into this and then use the same formula, or you can just know that the next thing for row 4 is -1, 0. That turns this divisor into a -1 curve, if this was a fan for toric variety. And then the next thing would be row 5. This is headed by 0, -1. Now, if I took this to be row 1, to be the next thing, row 6, if you will, which is the same as row 1, I'd actually have to put it here. This is the choice of the next ray, which will turn row 5 into a ray corresponding to divisor with self-intersection -1. Aha, it hasn't matched up. It's not a toric variety. And then if you try to continue, try to go to row 2, it turns out you get, it's the same, it's just the x-axis again. So this would be row 2. So we have 2 copies of sigma 1, 2. Here's sigma 1, 2. Here's sigma 1, 2. So if you want an affine manifold out of this, what you do is you just take this piece of paper, let's take the blackboard, you cut along here, and then you glue this cone to this cone isomorphically. So you just glue. Now, unfortunately, that's not something you can do with a piece of paper. It's an alpha. It's a shear. So you can't actually do that with paper. So you can't actually build this affine manifold in this way. That does turn out that the affine structure, it can be built. It's a cone. So you can just cut a wedge out of a piece of paper and then glue the 2 edges to get a cone, like an ice cream cone. But that's the affine manifold in this case. And as you can tell, there has to be a singularity at the origin. Otherwise, it would just be an R2. So generally I was kind of just drawing these things carelessly, but just saying there's a singularity at the origin. Now, I believe this is a different kind of singularity than you would have seen in Bernd's talks. In Bernd's talks, he would have put singularities along edges. And in fact, this picture is almost exactly the same picture as a picture that I think Bernd drew today, which is an affine manifold that looks like this, where you have these sort of standard types of singularities along 2 edges. And the way to think about this picture is it's the limiting version, where you bring these 2 points into the origin. And it's exactly the same picture. Okay, so that's the affine manifold. Okay, so the next step.
Can I ask a question?
Sir?
Can I ask a question?
Yeah, we have a question in the audience here. Go ahead.
When you look at these projective rational surfaces and you do this recipe, do you always end up not hitting 0, 1 if you're not toric? Is it always less, or is it always?
Yeah. So the question is, do we, if the surface isn't toric, do we always fall short, or could we also end up passing? We always fall short. And there's actually some fascinating sort of refined classification of what can happen, but that's going too far afield.
There's also a question here.
Yeah.
This procedure when you just take one your fat and then you glue it. So that you that's what you I saw that would be the kind of procedure one would do for like let's say a focus singularity. That's you seem to say that's not that nonsense. That's nothing. Here all the pictures are through Bernd. That you say that you already have two singularities and then
So, sorry, I'm only getting about 10% of that. Michelle, maybe.
Okay, maybe I can so I can different issues maybe during the answer. We insist to only have no, yes. My question was so limited knowledge I have of this of the picture where you say, okay, I take the fat and then well, it's not exactly and then I do and identify
Yeah. Mm-hmm.
components. So what I think is not a fact anymore, it's a point for a dog. And in my head, this would be the kind of manipulation I would do for focus singularities. But then you say, okay, it's similar to the other picture where you said the picture there.
Yeah.
And you said that now we already have two singularities and we push them at the origin. We have done it just already for one singularity, just for one focus singularity.
Yeah. So I mean, it's. Yeah, so I'm not sure if I've fully understood, so maybe it might be worth, once we switch to Skype for the questions, it might be worth returning that. But yeah, I mean, so a different example would have given just a single focus singularity at the origin. So if you take, for example, here's a favorite example, if you take P1 cross P1 with this toric boundary, you blow up one point. So again, this is a sort of simple example. Good exercise, check that this example gives rise to just a focus singularity at the origin. Now, really, so in general, these singularities could be somehow very complicated objects, far away from the sort of singularities you see in the integrable systems world. And one of the key points in my paper with Hacking-Keel is that you can factorize it. You can always factorize these singularities by pulling them apart into a whole bunch of focus singularities. So it's really just a way of hiding all the singularity information at the origin, but that choice of pulling apart is not necessarily unique. It might really give different answers if we apply the Gross-Siebert algorithm.
What would this choice?
So the choice has to do with the fact that there might be different rational surfaces with the same self-intersection numbers. And the construction I give is going to depend very vitally on the choice of surface. Okay. So Christoph, if that wasn't answering your question, why don't you ask once we switch to Skype and we can talk at greater length. Okay, so the next step is to build what we call the canonical scattering diagram. Okay, so this is another place where I can sort of quickly explain what's going on by using the technology I introduced. So let's focus. So I'm going to define, maybe I'll just draw it over here first. So a scattering diagram in this world will be just a bunch of rays coming out of the origin with some functions attached. So these are the, I believe you've seen in Bernd's talks, you've seen these kind of walls or rays or lines, line segments, which are going to govern things like broken lines, which tell you how things bend and how you cross these walls. So let's fix a ray D contained in, say, sigma I plus 1, a ray of rational slope. So here is rho I plus 1, and then we have the ray D, which I'll take as primitive generator of the ray AD, with GCD here, AB is 1. So I take a primitive generator. We can do that because D is rational slope. So we're fixing some cone, we're fixing a ray in the cone. Now I'm going to define a function attached to this ray. Okay, so I'm going to just write down an absolutely crazy looking formula, and then I will try to explain the various pieces. Exponential of the sum over beta over k beta in beta z to the beta xi minus 1 to the a, sorry, xi to the a, xi plus 1 to the b, and minus k beta, where I've not yet told you what any of these symbols mean. So I have to tell you what these mean. Okay, so first of all, so to make sense of this, first fix a monoid, a toric monoid, P contained in H2 in the second homology of X with the property that the only invertible element is 0, and if beta is in H2 of xz, represents an effective curve then beta is in P. So P contains the classes of all effective curves. Okay, so then I can tell you what the symbol z to the beta means. We write z to the beta in the monoid ring K bracket P. So we've chosen this P And K bracket P is generated by monomials of the form z to the beta. Okay, so that's what this means as an element of the ring K bracket P. Okay, what about all the other stuff? Xi and xi plus 1 are just variables I want to think of as associated with these rays. So xi, and it will become clear in a minute where these are living. So these are just living in some ring, which will be clarified in a minute. Okay, so now I need to tell you what this sum is over. So beta so we sum over all beta and p with beta dot dk. Let me use a different letter. Beta dot dl is equal to k beta times a, if L is equal to I, k beta times b, if L is equal to I plus 1, and 0 otherwise. Okay, so we're running over classes that have, at least numerically, have some fixed order of tangency with di and di plus 1, has fixed intersection number with di and di plus 1, proportional to a comma b. So k beta, this defines k beta, it's this constant proportionality. Where ab, recall, was this original choice of ab in here. Okay, and finally, so I think I've now explained everything here except the number n beta, and this is where log Gross-Hacking-Keel theory comes in. And finally, n beta is equal to the number of genus 0, one-pointed curves representing representing the class beta with contact order UP, where P is the marked point, given by K beta A, K beta B. So what is this saying? This is saying we're looking at curves. Let me just draw a quick picture here, what this might look like. So here, we're looking at curves which have one marked point which maps the boundary, and it maps the boundary in such a way that it's tangent to this divisor, to the order divisor di, the order k beta a, and it's tangent to the divisor di plus 1 to order k beta times b, and otherwise it doesn't interact with any of the other divisors. So to make sense of this properly, you need to do this in the world of log Gross-Hacking-Keel theory. Actually, in the original paper, we didn't have log Gross-Hacking-Keel theory yet, so you have to sort of do some jumping through hoops to avoid that problem and reduce to relative invariance, but we haven't talked about that. So think of this as an affine line in the interior, right? X minus d, so if you delete this point, you get an affine line, and the affine line maps into the interior of X minus d, at least generically. You might get some sort of degenerations where components start to fall into the boundary. But log Gross-Hacking-Keel, sorry?
I just write this k beta. That's like almost like taking the derivative, right? So, is there some in the formula for FD? Is there some quick way to
why that constant comes in. It seems to come in from gluing formulas. I don't think I have an easy answer to that question. But one's going to see in an example soon how wonderful that K beta is. Okay, so the other thing is that one can check, because we do have a dimension formula, one can check that this moduli problem is virtual dimension 0. And that's important because then when I say number of genus 0 one-pointed curves, I really mean the degree of the virtual fundamental class. Okay, so that all can be made sense of, and so we get these functions fd attached to the boundary. Attached to the ray. Now, let me. Because I'm tempted to show you how wonderful that K beta is now, so let me skip ahead in my notes for just a minute, do the example. So let's go back to the Del Paso surface of degree 5. So it turns out that the only possible way of getting such a curve in dp5 is to look at multiple covers of those EIs I showed you. Only possibilities are multiple covers of the EI. Okay, it's not immediately obvious, but you can prove that. So the thing is, you do have to worry about multiple covers. Is if you have one of these EIs, right? So that's certainly an EI is a perfectly good example of one of these kinds of curves. You have order of tangency 1 there, and it's just tangent to a single divisor. So in this picture, that would correspond to a ray supported on one of the rays. So D would be supported on one of the rays. So that would be rho I. But you also have to worry about multiple covers which are totally branched at this point. Because then you still have order of tangency, you still have a single point mapping to the boundary with some order of tangency k. Now, that means you have to deal with a multiple cover formula. And fortunately, I need more room for this. Let me keep this formula up so we can compare it. So f rho I in this case will be the exponential. So the only thing that matters is the degree of the covering. So I'll sum over k. And now k beta is just k. If it's a k-fold covering, you have to have k-fold order of tangency with a boundary divisor. So if k. And then we need to know what n beta is. Now that's a subtle computation because it's definitely virtual. You have a positive dimensional family with multiple covers. Fortunately, Rojo Pandurpande knows the answer to this, and it's -1 to the k plus 1 over k squared. So if k is 1, it's just 1. You have one curve of class EI. So then you get this z to the k EI, and then you get xi to the minus k. Now you cancel this, and then you notice that is the power series for the logarithm. And this is just 1 plus z to the EI xi inverse. Okay, so except for this constant, you've probably already seen in Bernd's talks, you've actually seen functions attached to the rays that look like this, 1 plus some variable. So that's,
Sorry, I was just wondering if you have a logarithmic theoretic way of calculating this possible couple orders? Because the way we did it with Raoul was with Bernd.
yeah, right. So,
Like having
yeah, so what I'm using here at the moment, I'm using comparison theorems between relative and Gross-Hacking-Keel theory, which has been done by the Gromov-Witten school, so there's no problem there. Ideally, we'd like to actually do this more directly without going back to GPS. And I know basically how it should be done, but it requires some gluing that still hasn't been completely worked out. So give us a few more years and it will be done. Okay, so that's the example. So how much more time, since we started late, should I go?
I mean, we're quite flexible with time.
Yeah.
Take all the time you want.
Well, that's a dangerous thing to say. Yeah, let me explain. Let me explain what, since I've introduced the scattering diagram, let me explain now what we do with the scattering diagram. So again, I think you will have seen this in Bernd's talks. But just to be somewhat more concrete, maybe I'll write this out. So the idea, of course, is that the scattering diagram is supposed to instruct us how to glue together various pieces, some sort of standard pieces to get some interesting variety. So what do we do with a collection, I call the collection D of rays? So here D is going to be just the collection of all rays of rational slopes with these attached functions. If the attached function is 1 because there are no Gromov-Witten invariants contributing, we could just throw it out because they won't do anything. Okay, well, let's pick an ideal, pick a monomial ideal. I containing K bracket T, such that the quotient ring such that AI, which is K bracket P modulo I, is Artinian. So it's just a little infinitesimal thickening of a point. Now, the goal is to build a scheme in fact, it will be an affine scheme flat over the spectrum of this ring. And we're going to do this, first of all, by gluing together some standard pieces. So I'm going to have one standard piece for each of the one-dimensional cones in the tropicalization. So for each divisor, for I equal 1 to n, let ui be the following scheme. So spec ai, then you join a couple of variables. So this is now where we are going to see what those xi's really mean that were in the formula over here. And I divide out by an ideal, which is xi minus 1, xi plus 1, minus z to the class of di, the I-family divisor, xi to the minus di squared times f rho I, where f rho I is the function, as we just saw over here, is the function attached to the ray rho I. Okay, so it's just a single equation, so it's a hypersurface in here. Right, this is a A2 cross C star or K star. So we're looking at a hypersurface in there. if I was the maximum ideal, so that the maximum monomial ideal, so this was just k, then of course z to the di would be 0, so this would disappear, and we just have a union of two, well, not by affine planes, but A1 cross k stars. So this is actually a flat deformation. Of something like A1 cross K star glued together by K star, so 0 cross K star with A1 cross K star. So it looks something like union 2, a normal constant variety, union 2 gadgets like that. Okay, and the z to the di tells you how fast you smooth. This is sort of encoding something about the affine structure. It's the same minus di squared we saw in the description of the affine structure, and the f rho I is perturbing the equation. Okay, so I want to leave this equation off for a second, so let me switch to this board. So these things have some canonical open sets. So if u, what I'll call ui minus 1I contains a ui, this is the locus where xi plus 1 is non-zero. Sorry, xi minus 1. So what do I mean? You just localize this ring at xi minus 1. And when you localize xi minus 1, notice this equation then allows you to eliminate xi plus 1. It's just a Laurent polynomial ring in two variables, xi minus 1 plus minus 1, xi plus minus 1. And similarly, you have ui plus 1, or ui plus 1 contained in ui. This is where xi plus 1 is non-zero. So we have canonically some thickenings of algebraic tori sitting inside this basic piece. So now what I want to do is I want to glue all these pieces together. So glue ui to ui plus 1. How do I do that? Well, I have sitting inside here this algebraic torus, ui I plus 1. And similarly, I have ui I plus 1 sitting inside here. These are canonically identified because it's spec of the same ring. I don't use that canonical identification. That's not going to give a good answer. Instead, I'm going to use I'm going to use an isomorphism, which I'm going to write as theta gamma d. So I think you've probably seen, in Bernd's talks, you've probably seen this kind of wall crossing before. So the picture here is we're in the cone with rays rho I and rho I plus 1. And inside that cone, we have lots of rays of the scattering diagram. Now, when you're working modulo a given ideal I, most of those rays just have the number 1 attached to it. The function is just 1, so you can throw them out. So they're really only a finite number of rays. And now what you do is you take a path, there's only one interesting path, from point over here to point over here, and you take a composition of automorphisms of this ring, or actually of the ring I plus 1. So theta gamma d is induced by composition of wall-crossing automorphisms. So when we cross the ray r greater than or equal to 0, AB, with the function f attached to it, we use the automorphism xi maps to xi times f to the power b, and xi plus 1 maps to xi plus 1 f to the power minus a. Okay, so this is just, I hope you've seen these things before in Bernd's talks. This is just made much more explicit. And the point is that what you do is you cross a whole bunch of walls, so you take the composition of these automorphisms in the order crossed. That gives you an automorphism of this ring, and hence a automorphism of this algebraic torus. And you glue together using that automorphism. So this gives a scheme, and I'm going to be almost done. Which is, I write as xi circ, because it's not yet what we want, over spec ai. This is flat because each of these individual pieces, each of these UIs is flat over spec ai, rather obviously, and then once we start gluing these together, it stays flat. So we have a nice flat scheme over spec ai. And not only that, you know what it looks like over the, so if you take the, it's an infinitesimal deformation of something quite simple, which is obtained by gluing together the pieces that look like this. So explicitly, xi circ is an infinitesimal deformation of something we call the n-vertex, so Vn minus the origin, where Vn is just Vn is just a union of A2s, which I'll write like this. This is a union of coordinate planes where I've indicated the coordinates on the plane. This is a sub-scheme of affine n space with coordinates x1 through xn. So what this is a flat deformation, some choice of flat deformation of the complement of the origin. Okay, so that's the first step in this. And now here's where the magic happens. I mean, so far I haven't used anything special about my choice of scattering diagram. I could have used an empty scattering diagram. I could have used all sorts of possible scattering diagrams. And so here's the main theory. Let's define xi to be the spectrum of the space of global sections of the structure sheaf of this scheme we just constructed. You just take all the regular functions on this scheme. That is, of course, this is an AI algebra, so we have a morphism to AI. And this is a flat deformation of Vn. Okay, so let me just end by saying this theorem really uses the fact that we chose the very special canonical scattering diagram. we need to be able to make this work. The trouble is there just may not be enough functions on this. In particular, one consequence of being flat is that any regular function, a flat deformation, any regular function on Vn has to lift to a function on xi circ. That's, if you use an arbitrary scattering diagram, there's no reason for that to be true. That's the magic of theta functions. We prove this theorem by constructing theta functions, which Bernd already described. Those theta functions are defined using broken lines. And we're then able to show we have enough functions here to show this is really a flat deformation. And then this is the mirror family, or if you want, you take limit over all I and get a formal scheme over the formal spectrum of completion of K bracket P. Okay, so I think this is more than a good place to end. Next time what I'll do, I'll say a bit more, do a bit more on the examples, and explain how we multiply functions on this, because then I will use that multiplication rule to sort of jump ahead to general mirror construction in all dimensions. Okay, so I'll stop there.
How is the audio this time?
The audio is not very good, so let's switch back to Skype.